In the 1920s, quantum theory was emerging as the best hope of understanding these strange phenomena. Its central idea was that atoms do not always behave like individual particles. Sometimes they merge together and behave like waves. They can even be particles and waves at the same time. This strange paradox was hard to accept, even for great minds like Albert Einstein. In 1925, a young Indian physicist, Satyendra Bose, sent Einstein a paper he had been unable to publish. Bose had attempted to apply the mathematics of how light particles behave to whole atoms. Einstein realized the importance of this concept and did some further calculations. He predicted that on reaching extremely low temperatures, just a hair above absolute zero, it might be possible to produce a new state of matter that followed quantum rules. It would not be a solid, or liquid, or gas. It was given a name almost as strange as its properties: a Bose-Einstein condensate. For the next 70 years, people could only dream about making such a condensate.
Matter can exist in various states. Atoms at high temperature always form gases. If you cool the gas, it becomes a liquid. If you cool the liquid, it becomes a solid. But under certain circumstances, if you cool atoms far enough to extremely low temperatures, they undergo a very strange transformation. They undergo an identity crisis. So let me show you what I mean by an identity crisis. When you go to low temperatures, the quantum mechanical properties of the atoms become important. These are very strange, very unfamiliar to us, but in fact, each one of these atoms starts to display wave-like properties. So instead of points like that, you have little wave packets like that moving around. It's really difficult for me to explain just why that is, but that's the way it is. Now, as you go to very low temperatures, the size of these packets gets longer and longer and longer. And then suddenly, if you get them cold enough, they start overlapping. And when they overlap, the system behaves not like individual particles, but particles which have lost their identity. They all think they're everywhere. This little wave packet over here can't tell whether it's this one or that one or that one or that one or that one, or it's there and it's there and it's there. They're all in one great big quantum state. They're all overlapping. They're all doing the same thing. And what they're doing, to a good approximation, is they're simply sitting at rest. This Bose-Einstein condensate is very difficult to imagine or to visualize. I could imagine what it's like to be an atom running around gaily, freely, bouncing into things, sometimes going fast, sometimes going slow. But on the Bose condensate, I'm everywhere at once. I've lost my identity. I don't know who I am anymore. I'm at rest, and all the other atoms around at rest, but they're not other atoms around. We're all just one great big quantum system. There's nothing else like that in physics, and certainly not in human experience. So just to think about this causes me wonder and confusion.
Dan Kleppner's group at MIT began to try to make a Bose-Einstein condensate in hydrogen.
As we started out the search for Bose-Einstein condensation, our enthusiasm grew because hydrogen seemed like such a wonderful atom to use. It had everything going for it. It had its light mass. That means that the atoms will condense at a higher temperature than other atoms would. The atoms interact with each other very, very weakly. All the signals seem to be pointing to the fact that hydrogen was the atom for getting to Bose-Einstein condensation.
Dan Kleppner's idea was to cool the hydrogen atoms by making use of their magnetic poles. He used a strong magnetic field to create a cluster of atoms in a cold trap. Unfortunately, sometimes one atom flipped another, which triggered a release of energy that raised the temperature.
It was a frustrating time for us because our methods were so complicated, we were having a hard time moving forward.